Let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. You guys are okay, and let's get to it. If you can turn your cameras on, I'd appreciate it. Kind of make things feel a little bit more personal. Especially, I think this class is one of the smaller classes, so that'd be nice. So let's actually jump into it. Where were we last time? Okay, so this is what we covered yesterday. Nothing according to the syllabus, but we went over what the class would look like and all that stuff, and we went through the syllabus and all that stuff. Some things I want to remind you about. Well, today we're going to do exponentials and log functions. I think we're only going to get to the exponential part, and we'll do logs on Friday. But the homework sections, hopefully you guys tried to get enrolled into that, as well as I did a poll to see was everyone getting communications from me via all the avenues that I sent communications. And I always do this. The computer actually has been acting up today. Okay. Back to communications. So I took a poll, and some of you didn't receive communications via all the ways that I sent communications. And I just wanted to make sure that if that is the case, that you should have emailed me. That being said, some people did email me yesterday. I didn't respond to everyone. So if I didn't reply to your email, don't worry too much about it. Because what happened is I also started getting brand new students getting into my classes and registering who weren't on my roster before. So to avoid getting confused and missing someone, I just decided I'll wait a couple days and then update everything all at once. So if you didn't get a communication through some avenue and you sent me an email, give me 2 or 3 days. Like if by Friday or Saturday, I don't actually send anything out, okay, I updated everything, then you can reach out to me again. But just leave that for a few days. Once I start to process new students and things like that, I'll just do it all at once. So I just wanted you to be aware of that. So let's actually get into the topic at hand. So we are going to talk about this. And normally I pre-type my lectures, but this semester I'm not doing that, just as I guess a way to pace myself. To make sure that I'm not moving too fast when I'm reading versus writing, and not just writing out examples. So I'll be writing everything out. So I'm going to put these lines in there so I don't like write off at an angle or something like that, because I think I'm prone to do that. Like I write at an upward angle for whatever reason with this stuff. But just for those of you who are probably new, I will leave this in the notes, just a link. When I save the PDF here, I think it saves everything as images, so it won't be clickable, but at least you'll be able to see it and get to the class website. So if anyone in this class is new, which I don't think so, I think all the new students I got went into my calculus class. But to get up to speed quickly, you want to go to the class website, find the syllabus there. You would also see a link to the lecture recording of yesterday's lecture. Anyone who didn't receive any communications from me because I sent it through 4 ways, send me an email, but don't expect me to respond right away. I'll respond roughly around the end of the week. Okay. That being said, let's actually jump into the topic, and we're going to move kind of slow, and we're not even going to do anything too crazy today. I mean, it's day 2. Let's not go too crazy. A lot of things I'm going to talk about, I believe that most, if not all of you, will already know about this kind of stuff. There are some implications that maybe you're not aware of, chances are, which I will go into. But for the most part, the math stuff, I think should be familiar to pretty much everyone. So yeah, I'll probably ask for some participation while I'm doing this. So let's start out with exponentials. AKA powers. And I actually want to start with the laws of exponents. Maybe I should tell you like what an exponential is first. Sometimes you guys will no doubt have seen things like this where we'd write something that's huge and then we'd write a little thing up to the top right corner. That thing is called an exponential. And the thing down here is called the base, right? So like x squared, we can call it x to the power 2 or x with exponent 2, x to the exponential 2. Okay, all right. So the exponent or the power is called the exponent or power of x. Okay, so that's basically what it is. Okay, and we've seen notation like that. I want to remind you of the rules, how these things behave under mathematical operations. So if I have one thing raised to a power and I multiply by another thing raised to the same thing raised to a different power, what does that become? You just talk back to me. I just want to make sure.
Is it x then a to like a b at the top?
A B?
Yeah.
Like that? No?
Is it a plus b?
It's plus, you add them, right? So you multiply things of the same base, you add the powers. What about division?
Subtract.
You subtract the powers. Of course, you can't divide by 0, so let's not forget that. What about if I have something to a power and I raise that to a power? What is that?
Do they then get multiplied? The A and
That's
the B?
when you multiply. That's the AB. Okay. What if I have two different things being multiplied and I raise that product to a power? Turns out that the powers will distribute across products. By the way, because they distribute across products, it's pretty intuitive to think that they would distribute across divisions, and they do. Right, you're not dividing by 0. It's very important that you note they do not distribute across sums, i.e., if I had x plus y raised to a power, it's not the same as x to the power plus y to the power in general. It's true if your a is 1, but it's not true otherwise, right? And this would work for a plus or a minus. So if there's a plus or a minus raising to a power, you can't just do this. But when it's multiplication or division, you can actually do it. You can distribute to each factor in the product, or you can distribute to the numerator and division and the denominator of a fraction. What other thing I wanted to remind you of? What does it mean if I have a negative in the exponent? So that's me waiting on you guys.
Don't you do the same thing except like you multiply x by, or you raise x by whatever a would represent, like negative every time, so the sign would switch like every couple times.
Not really, no. I mean, like, what would that look, how would you write it down? No. So I saw, I guess, in the chat.
Don't you have to move it to the bottom?
You move to the bottom, you take the reciprocal, right? So it's 1 over x to the a, right? Of course, your x is not equal to 0. And it's very important to note here, negative exponents do not affect the sign of the base. A lot of students think you'd have to put like a negative in front of this or something, but you don't, right? If the negative is in the power, it means take 1 over. It means take the reciprocal. Okay, so that's very important. And x to the 0? What if the power is 0? What does that mean?
Doesn't it just equal 1?
It equals 1, right? And your x cannot be 0 here either, right? Now, why is that 1? It's because, well, if I were to take anything divided by itself, I should get 1. According to our original rule, this means we should actually take the top thing minus the bottom thing. And so that would be x to the 0. However, because there's a division here, we can't divide by 0. So this rule works when our x is not 0. But that's where the rule comes from. That's how we know that raising to the 0 power gives us 1, right? As long as the base isn't 0, 1 is going to be the answer, because raising something to a 0 power is essentially dividing some other thing by itself. What is the other rule I want to make sure you guys know? Okay. Sometimes you forget these things because they're the obvious ones. Raise something to the 1 power, it's just itself. Here's something a little less obvious, unless maybe you've seen it before. What if there's a fraction in the power? What happens here? Go, that's you guys.
Can you make b like the root? When
B
you
is the root, yeah?
Yeah, and then a is the exponent.
Right. And we are allowed to switch these as long as your x is greater than or equal to 0. And that's because if your x is negative, there can be issues with taking radicals and roots, unless we want to, unless you're allowed to use complex numbers and things like that in complex analysis, which we're not. We're not going to be using complex numbers in this class. So we'll always assume that the base is positive, and that allows us to switch it. This means that we can compute things easier. So if I had 9 to the 3 over 2, I would rather take 9 to the square root before cubing the 9, right? I'm allowed to do it in either order. So that's very important. There is a mnemonic here, and it's called flower power. Yeah. I'm a grown man, and I still say this in my head when I'm writing this down. Flower power. Okay, so when you have a fractional exponent, the idea is to think of it like a flower, right? The bottom is the root. The top is the flower, which rhymes with power. Right, so flower power. The bottom number is the root. It goes on the radical, right? So your B is down here and your A is up there, right? So the a stays at the power and the b goes in the radical. Okay. So these are just the laws of exponents. This is how exponents behave under mathematical operations when the bases are the same versus when the bases are different. Let's actually jump into exponential functions. Okay, so let's talk about the generic form of such a function. This is something that looks like y equals a to the x. Okay, and here a is a constant. A greater than 0. And usually we consider a larger than 1. Okay. Again, the issue is when your base is negative, you can get into issues like if your x becomes a half, then now you're square rooting a negative number, and that brings up a whole other bunch of issues that we don't want to consider. So for us, our exponentials, our bases are always going to be positive. X is the independent variable. That is the input. And y is the dependent variable. That's the output. So let's see an example. So like y equals 2 to the x is an exponential function. Y equals 1/2 to the x is an exponential function. By the way, this is actually equal to that by law. What number did I make it? 6. You don't have to remember the laws in a certain order or anything like that. But I want you to appreciate that 1/2 to the x, I could write it as 2 to the x. So here, base is positive, but less than 1. But here, we can rewrite so that base is greater than 1. Okay, so that's what I mentioned here. We always want to think of the base as positive, but usually whenever we're developing rules, we're going to develop the rules for when the a is larger than 1. Let me be more specific what I'm talking about. Rules and graphs. So normally whenever I give you something like, oh, you should memorize these pictures, this is what an exponential function looks like. The implicit assumption is the base is larger than 1. So let's actually, first let's look at some non-examples. Say y equals x squared. This is not an exponential function. Right? Because the base is not a constant, right? And the power is not a variable. So 2 is always going to be 2, but the base is what's changing. That's not exponential. An exponential is when the base is fixed and the power is changing. And that's it's very important. So this is an example of what's called a polynomial. And the implicit assumption is that you guys know about polynomials. You're very good with polynomials, things like straight lines, quadratics, cubics, etc. You guys have a very good concept of it. So our syllabus actually starts with exponential functions, but you should know about polynomial functions somewhat. And I will actually discuss those in a little bit. Let's actually look at some graphs. So if our a is larger than 1. And remember, we can always assume larger than 1 because even if it's not larger than 1, we can rewrite it so that it's larger than 1. So what does an exponential function look like? If we were to draw a picture of it. I'm going to draw 4 pictures. And I mean, I'll zoom out afterwards, but I move this here. Okay, let's go back up here. Okay, so what does an exponential function look like? Well, if I'm graphing y equals a to the x, and my a is considered to be larger than 1, the graph looks like that. And it passes through 1 on this axis, because when your a hits 0, the output is 1. We have that from a rule, so that's what it looks like. That's the picture. If I were to draw y equals a to the negative x, this is a transformation that reflects vertically, or reflects over a vertical line, so the graph is going to look like this. Passing through 1 again. Okay. If I were to graph y equals negative a to the x, so now I make the base negative. What that does is it flips the graph, the original graph, upside down. So that is going to look like that. And if I make both the power and the base negative, it's going to flip the other one. So the graph is going to look like that. Again, this is passing through 1 and 1, not drawn to scale, obviously. Okay, so these are the pictures. And they're supposed to look relatively the same, but the curve is supposed to look the same. My first graph is pretty nice. That looks like a pretty nice exponential function. All the other ones look weird. Okay, here we can have x, y, x, y. Okay, so yeah, those are just some basics. Okay, so hopefully you guys have all of that. Some important notes. Note, exponential functions obey the laws of exponents. So that's why I told you the laws of exponents earlier. So if I have, say, so for example, if I have one function f of x, and this is, say, 2 to the x, which is an exponential function, and I have another function, g, where, let's make my input z, which is 2 to the z, then the function f times g, I can think of that as 2 to the x times 2 to the z, and I would get 2 to the x plus. right? So I can describe this function here would describe the multiplication of the other two functions. Okay? So if I have one output and another output and I want to multiply them, I would do it in a way consistent with the laws of exponents if my functions are behaving like exponentials. So that's something that I want you to be aware of. Also important to note, there's something I want to tell you before this, because when I tell you this important fact, I'm actually going to start to elaborate a little bit. So there's probably something I should tell you before. Another note, just a regular note, we can transform, and that's actually a technical term, right? So I'm talking about mathematical transformations, which is talking about linear transformations. And I'll state specifically what that is. Exponential functions to generalize them. I.e., I can have y equals, I can start out with an exponential function, then I can multiply by a number, and I can say add some other number, right? So B, C are constants. And that result is still considered exponential. What these things will do will just shift your graph around. If my C is positive, it's going to take the picture and move it up. My C is negative, it's going to take that same picture and move it down. The B, if it's larger than 1, it's going to stretch the picture vertically. If it's smaller than 1, it's going to squish. So this is still considered exponential. So example, so something like y equals 3 times 2 to the x plus 4. That's still an exponential function, right? It's going to look like that same picture that I drew above, except it'll be shifted around the xy plane in a little bit in a different position. So it would actually stretch it by a factor of 3, which for exponential functions, you don't actually notice that much, but it would shift it up by 4. So here is an important fact, and it's a commonly known fact, but I don't believe the implications are commonly known. So I'll actually elaborate on that a little bit. Exponentials grow faster than polynomials. I.e., an increasing exponential will surpass, as in its outputs will get bigger than any increasing polynomial. Okay, we can express this by saying something like the following. If I have a to the x, and I want to compare that to x to the a, I can write that the a is bigger, but I write like a double bigger than sign. And this basically means we're thinking about as the x is getting huge, like going off to infinity, and our a is bigger than 1. So the a to the x is bigger than the x to the a, right? As your x gets larger and larger. And x can represent all sorts of things. Sometimes x, the input, represents time. So you can say that over time, an exponential function is going to outgrow any polynomial. And so let's actually do a comparison. Let's compare y equals x squared, right? Your average quadratic versus y equals 2 to the x. Okay. Let's actually graph those. I'm going to take the time. Let's say I'm going to graph the exponential in red. And I'll graph the other guy in blue. So let me do that. What does x squared look like? This is where you chime in. And really, I want you guys to actually get in the habit of responding. So even if you don't know the answer, I would rather you say I don't know, or I would even prefer for you to just take a guess. Like I think it's this, but I might not remember, something like that. But it's very important that you engage, especially as business majors. You guys need to engage. So yeah, whatever. It doesn't matter if you're wrong. In fact, it's better that you get something wrong in class so that you don't go and get it wrong on a test when it actually counts, right? So it's better that I know what all the misconceptions are, if there are any. So yeah, just go. Like if I pause for a response, just say something. X squared, what does the picture look like? What do you think? What do you remember?
It's a U.
It's like a U, right? So, and it passes through the origin, yeah? So it'll look like that. Something like that, right? And the 2 to the x, we actually looked at that earlier. So that'll look like this. Right? Now, if you're looking for as these things are increasing, like as they're moving up, right? So you're focused on the right side of this picture. Here's something, not a lot of people realize much difference from that. Right? Yeah, the shapes are different, but they're kind of the same, right? So that is what this is called expectation. And not in a technical term. I'm kind of using this as a meme term, a meme term, M-E-M-E. So this is expectation. Doesn't look much different. Versus reality. So there's another side to this picture. So let me do this again, but now I'm going to kind of like zoom out. So now let's say I zoom out. So I'm looking at very, very big X, right? So this is going off to infinity. So I'm looking at a scale where my input is like a billion, cajillion, quadrillion, like something astronomically huge. Okay, so my 2 to the x is going to look like this picture, yeah? And I know it's gonna pass through whatever down there. Okay, on this scale, what would the x squared look like? What do you guys think?
Just half of you.
Just half a u, right? Which is very common to think. It's actually not correct though. The x squared is still a u, don't get me wrong. This is what x squared looks like. But when you zoom out on a large scale, how is it going to look by comparison? It's going to look like 0, like it shouldn't even try. Why does x squared even wake up in the morning? It's not going to beat the exponential, right? X squared is effectively 0 for large x compared to 2 to the x. And by the way, 2 to the x not just beats x squared. If I had x to the million, the same picture would result. If I had x to the billion, the same picture would result. X to the trillion, the same picture would result. Now, it might take a while for you to notice that happening. Like it'll take a lot longer for you to notice something like this happening with x to the trillion than you would with x squared. But in the short, the idea is they look similar in the short term. Right? So that was the picture up here, right? So yeah, the x squared is like a u, the 2 to the x is like that thing. Yeah, they look relatively similar. And I suppose if I were to zoom out, they would also look relatively similar. The x squared is going to be like a u. And that is, quite frankly, a very normal intuition. It's very intuitive to think that way. And that's the point that I'm going to try to make here. And this is very, very important. And this is one of the reasons, so that this is what I'm going to elaborate on, because things like this fact that I wrote up here, that exponentials are larger than polynomials. Any calculus student knows that. Any engineering student knows that. Anyone who actually deals with exponentials and polynomials for any appreciable length of time, but the exponentials are bigger than polynomials. But it does not mean we understand that at an intuitive level, because most people, if I were to draw the picture on a large scale and ask them, what does it look like? They would tell me the same thing. Oh, it looks like a U. Well, no, on a large scale, it's going to look like a straight line. It's going to look like it's not even doing anything. And that is super, super important. And this is one of the things where we get into this situation where students will learn some mathematical fact in class, and they never really understand what the implications are. They just know the maxim or the rule, and so they go through all their math class, and they're like, oh, math class was a waste of time. Like, it never helped me. Like, I never used the math that I learned. But it's because they don't notice it happening. So here's a real world implication of what this actually means for you. So I'm going to just talk about some examples that I'm sure you guys actually have some experience with. You ever realize how the ultra rich just seem to get ultra richer? You ever notice that? Like, you can have this guy with billions of dollars, and he literally goes to into philanthropy, gives away millions of dollars, billions of dollars, and then somehow the following year he's richer than he was the last year. And people are like, how is this possible? This guy's like, he's not even really working anymore. He spends most of his time giving his money away. How is it that he's getting richer the following year? It's mind-boggling. It defies intuition. And the reason is the ultra-rich tend to have their money in places where it grows exponentially. And so it doesn't make any intuitive sense to us, right? So most people who are not ultra-rich, their money tends to grow linearly or something like a polynomial. So yeah, if we splurge 1 month, then we're in trouble for rent the next month for a lot of people, right? Whereas this person can literally give away millions of dollars and he's richer the next month. The difference is someone's money is growing like a polynomial, the other person's money is growing like an exponential. And it matters, and especially on a large scale. Now, yes, if that person had their money in an investment that was growing exponentially, but they started out with a bank account the same size as your bank account, you guys aren't going to notice much difference. If both of you splurge 1 month, you're both going to be pretty much in the same situation the next month. However, if you have someone who already is far along the time scale and they already have $1 billion and that is growing exponentially, then they can splurge a lot 1 month and their money is growing at such a rate that it's like not even noticeable that they lost money the previous month. And you're going to like, what happened? Of course, conversely, we all know stories like when you have this super rich person, but they lost it all, on women and drugs and partying and whatever. And they had hundreds of millions of dollars and then suddenly now they're broke. And you're like, how does that happen, right? Which is also a strange phenomenon. Well, usually, not always, life is complicated and there are many situations, but usually that is a rich person who did not have their money growing exponentially. So their money was growing more like a polynomial. So it's pretty easy to go to zero over time. And so the idea is what we can take from this as a real world example to get away from the math is if, for example, you want to grow your money, you need to have your money in a situation where it is growing exponentially. What the math tells us is that saving money under your mattress is a bad idea, right? Saving money in a checking account is a bad idea, right? If you are saving, say, $100 every month, hiding it under your mattress, your money is going to grow like a polynomial. In fact, it's going to grow like a straight line. It's going to look like this. And yeah, it's going to look like you're doing better every month. However, zoom out and it's like you're not really doing anything, as opposed to another person who saves $100 every month, but instead of saving it into a checking account or under their mattress or even the typical commercial savings account where it's growing by like 0.01% per year or something like that, which technically is exponential, but it's so slow you're not even going to notice. You're going to be in this situation for your entire life, and you're never actually going to notice that growing. But someone who invests that same $100 in some investment that grows, say, 4% per year, 8% per year, 10% per year, in the short term, you're not going to notice much difference. Their bank account is going to look very similar to yours. But if you walk away for 20 years, 30 years, and you come back and look at both of your bank accounts, the difference is going to be mind-boggling, right? And this is why people like Einstein said, the compound interest is one of the great wonders of the world, because it's mind-boggling. As human beings, for whatever reason, we're not good at conceptualizing exponential growth. We're good at conceptualizing linear growth. And so a lot of people make bad decisions because of this. And a lot of people rather not take certain risks because of this. However, anyone who knows the math would know the risk to get exponential growth is worth it, especially over time. And that makes a difference. That makes a lot of difference in reality. So yeah, I can talk up to you about the math and what this is and what the pictures look like, but the real world implications are huge. And this is going to mean a lot for the decisions you make with your money and with other things. And knowing opportunities that growing exponentially versus ones that don't, you should understand the difference is huge. You should also understand in the short term, you're not going to notice the difference. The difference appears in the long term. The guy who's saving $100 under his mattress and the guy who's putting $100 in an investment growing 4% per year, in the short term, they look pretty much the same. By the time they're retiring, though, one person is going to be a millionaire and the other person is not. And they're making the same sacrifice. They're both putting in $100 per year. But the difference between these two people in the long term is going to be very, very different. And that is very, very important for you to understand. So that's why I say it's an important fact, but I wanted to move it from just a fact about mathematics to a fact about just, something that you can actually use to make decisions. Okay. And I know we're a little bit out of time, but I just want to take a few minutes to talk a little bit more about stuff because I did it with the other class. And so I want to do it with you guys. So let's actually talk about a real world example. And I'm just going to conceptually explain this stuff. I'm not going to get too mathy into it. We'll do that tomorrow, Friday, as well as later. Compound interest. Okay, so suppose you have $100, or you invest $100 into an account growing I just want nice round numbers because I just want you to get the idea. 10% per year. Okay. So in the beginning, right? So we start. You have $100. Now, at the end of year one, you're going to have that $100 plus you're going to get 10% of that $100 added to that value. Does anyone know what 10% is as a decimal?
Point one. Is it 0.1?
It's 0.1, right? You should remember that percent means divide by 100, right? So 10% means 10 divided by 100, which is 0.1. 50% means 50 divided by 100, which is 0.5, et cetera, right? So percent means per century. Per means divide, century means 100. Okay, so that's actually 100 plus 0.1 times 100. In other words, at this point, you would have $110. Okay. Now, at the end of year two, now you have $110. That's going to grow by 0.1 of $110. You will notice that that is 121. I want you to appreciate that it grew by $10 the first year, but it grew by $11 the second year, right? So even if you change nothing, it actually grows by more and more over time. And this is why it beats something like linear growth. It's not growing by the same amount every time, right? So it's not always growing by $10 every year. With every passing year, it grows by a larger and larger amount. So it stacks on top of itself and it compounds, right? Now, there's a nicer way to express this. And at first, it's not going to look nicer, but you're going to see why it's the nicer way to express it. Instead, let's look at it this way. So if I had 100 plus 0.1 times 100, what you can do is the 100 is a common term, so we can factor that out. We'd be left with 1 plus 0.1, right? And it's actually nicer to express it this way. Why is that? So at year three, what's going to happen? Well, now if I have 100, if I have that amount of money, then I'm going to grow by 10% of that amount of money. Right? And so now what's going to happen is this is now the common term, and I can factor that out. And I'd be left with 1 plus 0.1. You'll notice that these are the same. So laws of exponents says if I multiply things of the same base, I add the powers. So now I get a square. And you can now see the benefits of writing it in this way. Now I can tell you at year n, I would have $100 times 1 plus 0.1 to the n minus 1. Right? And we tend to look ahead. So we look like 100 plus 1 point. We tend to look to the following year over time. Okay. And that's because, if you put your money in the bank today, they don't count the interest on your account until the next year time has elapsed. So you kind of look ahead in finance. Okay. So this leads to the compound interest formula. So what you'll notice is the money after some time, if you start out with P dollars, which is like 100 here, it's going to grow by 1 plus some percentage over time. Now, sometimes we can add interest several times throughout the year, and this is talking about compounded n times per year. So you can divide that interest up into n parts, and you add that interest to the principal n times per year, and so you get that in the power. And so this is called the compound interest formula. And here, A equals balance after T years. P is what we call the principal, which is the initial amount. R is the interest rate. N is the number of times compounded per year. Okay. Note, if P, R, N are fixed, meaning it's I just leave the $100, I'm always getting the same interest rate, and they're compounding it the same number of times per year, and none of that is changes, this gives an exponential function, because the only thing that's changing is the power, which is the t. So the base is going to be a constant, but the power is changing, and that's an exponential function. Compared to, say, I have $100 growing by K dollars per year, right? So this is the guy putting his money under a mattress, right? So this is going to grow by 100 plus. For every passing year, we would add K dollars to it, right? So after T years, so this gives you A equals P plus KT for linear growth. So in other words, saving your money in a checking account grows like this function. Saving your money in an investment that gives you interest grows like this function. Now, these two functions, in the short term, their values are going to seem pretty similar. In the long term, though, the values are going to be very different. And this formula is a very important formula. Einstein even commented that compound interest is one of the wonders of the world because it defies reason. It looks like it's not doing much different in the short term, but eventually it's like, wow, right? So it's like exponential functions like really mess with humans' heads. So next time I'm going to do some examples on this stuff, but I just wanted to wrap up there with introducing the compound interest formula. We will see this again when we do the finance section of the class, but for now, that's where we're going to stop. So unless there are any questions lingering, I think we'll sign off now. Okay. All right. We will stop there. I will see you guys on Friday and we will continue the discussion. Thanks for your attention and I'll see you in the next one. Ciao.